is Omur Arslan from Penn?
Yes, partial of Penn.
You can fill in.
Yes. Okay. Hi everyone, I'm Omur Arslan, and today I will introduce a simple algorithm for coverage control of panel zoom camera networks. And this work was done at the University of Pennsylvania with master student Hancheng and my advisor Dan Koditschek. Now I moved to Germany, start as a postdoc researcher at the Max Planck Institute for Intelligent Systems. And this work was motivated from the following observation. We have cameras everywhere for surveillance purposes, and they generate vast amount of data, which makes the life of a human operator really terrible, because processing all the information and making the right decision for each camera to look at the right point is a difficult task. So in this work, our goal was to automate this process. So we assume that all this information coming from the cameras are processed, some activity distribution over the environment is estimated, and the next question is how we need to reconfigure our cameras. In this work, we were motivated by some standard knowledge on coverage control of mobile sensor networks. In such settings, a simple idea like applying Voronoi diagrams based on sensor location solves the optimal sensor allocation problem, and simply steering each sensor towards the associated Voronoi centroid solves the coverage problem in a locally optimal manner, and in practice we usually obtain good coverage configurations. And we would like to have similar construction for cameras, but cameras have some directionality and resolution constraints, so we need to develop proper sensing models, the appropriate sensor allocation algorithms, and if it's possible, similar nice, simple, intuitive algorithms to control camera perspective and zoom level. So in our setting, we assume that we have a set of cameras at some fixed locations to cover a convex environment. So these cameras have variable angle of view corresponding to zooming in and out, and a variable optical direction to control the camera perspective. We consider two factors that affect the sensing performance of a camera. One is the view perspective. So we assume that perspective quality decays away from the optical direction towards the boundary of the angle of view. So animation is illustrating this quality measure. Here, red is good, it is high quality, and blue is bad, it's low quality. And intuitively, it is consistent with physical nature of the cameras, because we usually have increased lens distortion away from the optical axis. Also, usually computer vision algorithm suffers from the incomplete and partial information around the boundary of angle of view. So the second factor is the resolution constraint, because cameras have finite resolution, and usually, again, computer vision algorithms detect certain type of object at a certain depth, and if the object is too close or too far away, then the sensing accuracy estimation quality decreases. And the other factor is if you zoom in, which means that if you increase the angle of view, the sensitivity of the camera decreases. So in our resolution quality, we try to encode this using Gaussian and the beta functional forms for both unlimited and the limited range sensing. One can think these two quality measures as probability of event detection probability of the cameras. So if we assume that they are independent, the overall sensing quality of a camera can be designed as the multiplication of perspective and the resolution quality. Again, in the animation, I try to illustrate how the spatial sensing quality changes with changing angle of view. So we all know that all models are wrong, but some are there useful. And in the rest of the talk, I will try to show that these spatial sensing qualities can be useful to determine optimal sensor allocation and identify optimal sensing configuration of panel zoom cameras. So let me start with optimal camera allocation. So we have our sensing model, and we will follow a standard approach where we assume that the environment is partitioned into some dominance region for each camera, so that each camera will be responsible of the associated dominance region, and accordingly a standard coverage objective can be designed as the total coverage quality over these dominance regions of the cameras. And one can intuitively observe that if each event location was assigned to the camera with the maximal sensing quality, then you will obtain the optimal partition of the environment for sensor assignment. And this defines a generalized form of Voronoi diagrams, and we call them conic Voronoi diagrams because they are generating objects as camera cones shown on the left bottom. And if you just use the perspective quality, you obtain the partition of the visible region as shown in the middle. And if you use the spatial sensing quality, you obtain the partitioning of the region as shown on the right. And I believe that they are very intuitive and make sense to use such a sensory assignment of camera sensors. So we know the optimal sensor allocation. The next question is, can we find some explicit specification about the locally optimal coverage configuration, which means that can we specify some geometric conditions on angle of view and the camera perspective. So I will summarize the result for unlimited range sensing, but the result also applies, similar result applies to limited range sensing model as well. Here, it is useful to design some Voronoi parameters because we have some event distributions, and we already have we know the optimal coverage, optimal sensor allocation is given by the conic Voronoi diagrams. One of the important Voronoi statistics is the centroidal Voronoi perspective. It basically says that for every point on a camera's Voronoi cell is a candidate perspective to look at. So if you take all the average of, a weighted average of all these candidate camera perspectives, you obtain the centroidal perspective, centroidal Voronoi perspective. And associated with centroidal perspective, we can also define a centroidal angle of view. And why these terms are important? Because we can write the change in our objective function explicitly in terms of these Voronoi statistics. And more importantly, we can characterize the local optimal configurations of a camera network. Basically, it says that at a locally optimal configuration, cameras should look at the Voronoi centroidal perspective with the Voronoi centroidal angle of view. So if we know what is the best, we just need to design a control policy. Here we assume first order discrete time and the continuous time camera dynamics and propose some simple coverage algorithm that will asymptotically bring our network to the optimal coverage configuration. To get some intuitive understanding of our construction, I would like to start with on a single camera, and assuming that there's a uniform event distribution, which means that we would like to do the area coverage. In this case, camera tries to move in order to maximize its visible region, the volume of the camera cone. But basically, it can go all the way to 180 degrees, but there is a trade-off between the sensitivity and the volume of the camera cone, and we optimally balance here this quality. And if you have some event distribution concentrated in some part of the environment, then the camera goes and looks towards that event and zoom in to focus on the environment depending on the variance of the activity distribution. Second illustration can be what happens if you have the multiple cameras. Of course, they will try to cover the entire space. Again, there is a trade-off between the sensitivity and the volume of the covered region. So here the cameras try to choose the best balance based on our coverage objective. If you have the some event activity distribution over the environment, the cameras are focusing on those part of the environment where you are most likely to see some activity distribution. And we also demonstrated these results using some experimental setting at Penn. We had a camera network consisting of 6 Pentel zoom cameras, but for ease of the visualization, I just showed the result for 3 cameras. Here we use April tags to define some artificial activity distribution in the environment, which defines a Gaussian mixture model where each Gaussian is centered at the April tag locations. And cameras are just started from an arbitrary initial condition, and we just follow our coverage policy. At the end, we observed that 2 of the cameras are focusing on the April tag location, and the 3rd camera, the red one, is looking at the region between them, and these were not hard-coded behavior. They are just emerging out of the design we perform here. So in summary, our contributions can be listed as follows. So we define some heuristic, but I believe that very useful spatial sensing quality measures for cameras that are consistent with the physical nature of the cameras and limitation of computer vision algorithms. Using these spatial sensing measures, you can naturally define some Voronoi diagrams, conic Voronoi diagrams to determine optimal camera allocation. And using the associated Voronoi statistics, it is easy to define a simple greedy strategy to obtain optimal coverage configuration of Pentel zoom cameras. So I will finish here. If you have any question, I will be happy to answer them now, or we can continue further discussion tomorrow at the poster session. Thank you.
Very nice, thank you. So if you have a question, please raise your hand up high so we can see you with a microphone. Right there. Okay, so we have 2 questions.
Hi. What happens if the environment is non-convex?
So it's a good question. Why we need the convexity? I guess it's just needed for the proof, you know, to follow a kind of a nice continuity properties, but you can apply the same ideas in non-convex environment. You need to be a little bit careful about the occlusions, because non-convex environment usually comes with the occlusions. As long as this modeled, I believe that the extension of this work will address those questions, and you will obtain similar intuitive algorithms. You need to, again, identify what is the centroidal perspective, and then steer the cameras towards those centroidal, perspective and the angle of view. But current work just try to identify these, provable properties first. Extension will address those non-convex environment and occlusions. Yep, please.
Very, very interesting work. I was wondering, how would your algorithm adapt when you have a dynamic configuration of those events, for example, as if it was given by a visual attention algorithm? Do you think you would need to modify anything in the algorithm, or would it work just out of the box?
Actually, it's a good question. I believe that it will work out of box, because you can think that you have a stationary target point here and you are trying to navigate towards it, but now you are moving it. Everything is well defined, so the Voronoi statistics associated with the sensor allocation with dynamically changing, because the activity distribution is changing, and this is the reactive nature of such constructions. They are model-based, there is no learning, but they are reactive, what's happening in the scene. And this is another goal. Hopefully, we would like to combine how we can do the vision-based activity estimation and do the coverage control and actually balance the area and event coverage. This is an interesting problem domain, I believe.
We have time for one more question. So I have one. If you were allowed to move the cameras, which approach would you use and how would you integrate it with this work?
So it is also a nice feature extension. Actually, in our motivation in the paper, we say that our main goal is flying cameras. So we want to do the same thing. And here the spatial sensing model directly applies. And I guess all the results should work. Just you need to use some integration of the some results I initially illustrated in the first slide. We already know how to move a mobile sensor, but here a visual sensing model will be through the camera. So I guess similar things will apply. So we will have move to centroid-like strategies for camera locations, and the rest will directly work to adjust where you need to look, to adjust the perspective and the zoom level. But I think it requires a little bit more careful work regarding to provable properties if you are gonna diverge. But in this setting, I believe there is no reason for divergence because we always have a certain desired depth. So there is no reason to cameras to fly away too, you know, because it is one way to go really far away from the scene so that the sensing volume will increase, but the desired depth will balance this thing, but we haven't looked at it that carefully.
Okay, thank you very much. Thanks, speaker again.